In the last lecture, we saw how we could get useful information about what was going on at a point where a function was undefined by looking at what the function was doing at values really close to that point. Now, today we're going to start moving in the direction of a formal definition by first looking at an informal one. And that'll give us something we can use to analyze some simple test cases and to get confident that we're going in the right direction before we try to come up with something more formal. So this is my informal definition. And I know it's a math definition. It's a little wordy, right? One thing that I'm hoping people take away from this class, besides the obvious calculus skills, is a little better understanding of how to read math. And I know most people, if you're taking a class and you're reading the book or whatever, and you see something like this and your eyes glaze over a little bit, and I'll just wait for somebody to explain it to me. You kind of need to start moving away from that. Right? When you see things like this, take a minute, read it over. Try to understand what it is it's saying. Some people, a lot of you, as you go forward, you're going to be taking more and more math classes, even if you're doing a science or engineering kind of degree. You need to get a certain skill, a certain ability to read these things and get a basic understanding of what they mean. So let's see what we have here. If the values of f of x, okay, that's the function, are close to L, and just so we're clear, L is a number when x is close to A. Okay, A is also going to be a number. And this is a really important point here where we're going to circle back to this when we look at some examples, but not equal to A. Then L is the limit of the function. Okay, and this is how we write it, right? You've got that LIM, you see that you think limit, and that arrow, you kind of read that arrow as approaches. So the way I would read this, I would say the limit of f of x as x approaches A is L. Right, so that's the language we're going to use. Okay, now I know it's wordy, right? But so let's look at some examples, right? Anytime I'm reading something new like this, right? That's one of the first things I do, right? Let me come up with some examples, see if that helps to make it more concrete for me. So I've got some here, right? And you know, so I've got our definition, our informal definition at the top there. And what I'm looking to talk about in these three examples is the limit of f of x as x approaches 2. And what I'm saying here is I'm saying that for all three, then you'll notice they're all fundamentally the same line, right? I've just kind of made some little tiny changes on the second and third one. All right, so what I'm saying is that for all three of these, the limit needs to be 3. All right, so let's look at my limit statement here. First, let's pick out some pieces. This 2 is the A in the limit, and this 3, that's the L in the definition. All right, so look at the first one here. This is just a plain old-fashioned, very well-behaved line. Okay, so what my definition here is saying is if I pick an interval, we're talking about the limit as x approaches 2. So I'm going to go to 2, and I'm going to pick an interval around 2. Right, kind of a range of numbers, some on each side. What this definition is saying is that for 3 to be the limit, every number in this interval around 2 has to be mapped to a number in a corresponding interval around 3. And you can kind of see this happening, right? If I pick a number in here, I'm going to pick a number kind of over on the edge, right? And I go up to the function, f of that number is this number here. And I suppose I pick a number from the other side, right? Let me go over here someplace to the right of 2, but let's pick something close to it. And if I take this number and I go up to the line and I take f of that number, I get that point. You see how I'm kind of staying close to 3, right? And if you let's just think about the endpoints, right? If you pick the endpoints here, this endpoint goes up to here, and this endpoint goes up to here, and you can see, hopefully, visually you can see, if you pick any number in this interval around 2, its corresponding y value is going to be in this interval around 3. That's what we're talking about, right? That's what this definition is saying. Okay, let's look at the second one. This one is a little different. The function is defined at 2, right? But there's this weird hole. Instead of being that nice, continuous, nice, smooth line, now there's this jump. Okay, so let's kind of work through my example again here, right? If I take an interval around 2, and I kind of jump up here, right? And I look at the corresponding y values, I get this number. And if I look at the upper end, I get this number. And now you see there's a problem. There is a y value that is not in this range here. It's this one. Okay, and I'm all right with that. That is our special exception here, right? Every value close to A has to get me a y value close to L, except for A itself, right? That's the one exception. That one point, x equals 2, does not have to go inside that interval. So you see, this limit is also equal to 3 because of that special exception. Every other point in this range goes to this range. Okay, and how about my last one? Right? You see, we've got this now. Now the function isn't defined, never mind gaps or things that are just kind of out of place. This function isn't defined at 2. It doesn't even exist there. And again, I'm okay with that. If you pick any interval around 2, every x value in that interval gets mapped to this interval except for 2, and that's okay, because my definition says that's the one point I don't have to worry about. Okay, so this is the idea, right? This is the general idea that we're talking about here so far, right? So we'll make this more precise in a little bit. But for now, let's look at some examples. Right? Take a look at this thing. I'm claiming that the limit of x as x approaches A is just A. Okay, let's see what's going on here. First, this is the function, right? My function here is f of x equals x. Okay, well let's graph it. Everything we've been doing is pretty visual so far, and that's been working for us. So let's continue that. I'm going to come over here and I'm going to graph f of x equals x. That's just this 45-degree diagonal line. And then let's pick a spot. I'm going to just put right here. X equals A. Okay, so, and I'm going to be a little more precise about what the theorem says. It's not a theorem. What the definition says. The definition, and it's the way we have to phrase it in English is a little backwards from the way we really do this in math. I'm going to pick an interval around L. I'm going to pick an interval around my limit. And I'm going to show that there is a corresponding interval on the x-axis that takes every number into it. Right? In practice, this is what the definition is saying. We start with an interval on the y-axis and find a matching interval on the x-axis. Okay, so let's do that. I'm claiming that the limit is going to be y equals A. Okay, so here's what I'm going to do. I'm going to take an interval, right? I'm going to take an interval around that y value. And we talk about these intervals being small. If this happens for big intervals, it's not very interesting. We need it to be true for every interval, even little tiny ones. So here's what I'm going to do. I'm going to say, look, let this point here be y plus epsilon. And I'm going to let this point down here be y minus epsilon. Okay, we need a quick Greek lesson because we're going to use these two letters a lot. This kind of curly e, that's the Greek letter epsilon. And this kind of curly d, that's delta. Right, we use these two letters. Usually we use them to represent some small number. All right, so let's see what's going on here. Let me move this down just a little bit. Get this out of the way. I'm going to put it over here. Y minus epsilon. Okay, so what x value corresponds to y corresponds to y minus epsilon? Well, remember, f of x equals x. So the corresponding x value here is also x minus epsilon. And the same thing happens over here, right? The corresponding x value here is x plus epsilon. So every number in this interval is being mapped into my y interval, and that's what I needed to be true, right? That's what I'm looking for with my definition. So that and again, informally, this is by no means a formal proof of this yet. We're going to get there. But for now, this is telling me, yeah, this is good, right? My definition is doing what I need it to. So let's look at another example. In fact, I'd like you to think about this one for a second, right? See if you can kind of figure this one out. All right, so first let's be clear, right, what our function is. Our function is f of x equals c. It's constant. That's y equals a constant. All right, well, what's the graph of y equals a constant look like? Well, it's a straight line. It's a horizontal line. So let me draw a horizontal line here, right? And this will be our graph. The graph of our function, f of x equals c. Okay, so, and where's my limit? We're getting to the point x equals a, so let's put that, just kind of picking a random spot, arbitrary spot to put it. Now what I'm saying is, I get to pick an interval around c, and you have to give me an interval around a where all of the numbers inside there get mapped into my interval. Okay, so let me do that. I'm going to pick an interval. I'm going to call it y. I went down there, didn't I? That's y minus epsilon, and this is y plus epsilon. Okay, so you need an interval around a that get maps entirely into there. Well, like this really should be nice. Pick any interval that you like, right? I'm going to pick, keep it simple. I'm going to do a minus 1, a plus 1. Every number in that interval gets mapped onto, not only into the interval of that point, it gets mapped directly onto that point, right? So this shows what I'm looking for here, right? The limit of a constant is always going to be that constant. So take a look at this thing now. Okay, that's messier, right? There's a whole lot more going on there. And hopefully, the first thing that stands out to you, I'm asking you for the limit as x approaches -1. The function isn't defined there. If you put -1 into that denominator, you get -1 plus 1, that's 0. And that ain't happening. So the function isn't even defined at -1. But remember, this is why our definition explicitly says, I don't care what's happening actually at -1. That's the one point where the function's value doesn't have to be in my interval. Okay, so let's see. I mean, anytime I see something like this, always my first thought is, can I simplify it, right? And I think I can here. Let's factor that numerator. This becomes the limit x approaches -1, x plus 3 times x plus 1 over x plus 1. You see, that's good, right? The x plus 1's cancel. So not only is it simplified, but I eliminated the factor in the denominator that was causing the function to be undefined. All right, so what am I left with now? This is the limit x approaches -1 of x plus 3 equals 2. All right, well, let's kind of go to our standby here. Let's graph this. I'm going to graph x plus 3. That's a y-intercept of 3 and a slope of 1, so it's going kind of like this. And this way it's going kind of like this. Okay, so there's my graph. And I'm talking about that's not my graph. Sorry, there's a hole right there, right? Because we put a hole in the middle. There we go, because the function isn't actually defined at -1. Okay, is that a problem for me? Well, I don't think so, right? Pick an interval around 2. That's my L, right? That's the number that I'm claiming is the limit. So pick an interval around 2, right? And if you kind of back this over, you get to here, and you get to here. Every number in this x interval is being mapped into this y interval. So let me be more precise. Every number in that x interval around -1 is being mapped into a corresponding interval around y equals 2. And that's what I needed to happen, right? That's why this limit is, in fact, equal to 2. Okay. So we've seen a bunch of examples where the limit exists. Right now, let's take a look at this guy. Here, hopefully, again, you immediately see there's a problem. If you put 0 in the denominator, this function is not defined there, right? Because the denominator can't be 0. So what does this look like? Well, you can experiment this with a little bit if you like. What this looks like is there's a line here, a horizontal line, at y equals 1. When x is positive, the absolute value of x is just x, and the function is x divided by x, which is 1. Now on the other side, when x is negative, then you're going to get this line, right? And this function is undefined at 0, so I have to put an open circle on each of those spots. Okay, now what I want to show here, what I want to convince you, is that this limit in fact doesn't exist. Right? These limit, I know we've been doing a lot of stuff where we had functions where it was undefined and there were holes and all sorts of things, and we were still making it work. There are situations where you can't make it work, and this is one of them. Okay, so let's see why. I'm going to, and here I got to pick a number to be our test. And there are two obvious possibilities. I can say, well, maybe the limit, and I'm going to put a question mark here, right, because I'm not sure. Maybe the limit is 1. Okay. Well, I don't know. Let's see about that. I have to pick an interval around 1. And now I have to find an interval around 0. Remember, that's my A right here. I have to find an interval around 0 where all of the numbers in that interval get mapped into that interval on the positive y-axis. And there isn't one. Right? There isn't one. No matter how small an interval I pick around 0, any number over here on the left-hand side is going to -1, not +1. Right? So this can't be 1. Right? Let me clean this up a little bit. Suppose we try. The only other obvious kind of candidate here is -1. Well, but -1 has the same problem. Pick an interval around -1. Okay, no matter what interval you pick around 0, all the numbers on the right-hand side are going all the way up there to +1. They're not inside your interval around -1. Right? So this is an example of a function where a limit doesn't exist. So this one is a little stranger. We've got some trigonometry here now. Hopefully you see the problem pretty quickly. The function sine of 1 over x is undefined at 0. You try to put 0 in for x, you get 1 over 0, and that can't happen. So what are we going to do here? Let's think about this. When does the sine of 1 over x equal 1? All right, well, that happens when 1 over x equals pi over 2 plus 2k pi. And let's see, I'm going to add these fractions together. So let's make this 4k pi over 2, give it a common denominator. 1 over x equals pi plus 4k pi over 2. And now I can just flip both sides over. X is equal to 2 over, and I'm going to factor a pi out of that, what's now the denominator, pi times 1 plus 4k. Okay, well now let's look at some numbers. When k is equal to 1, x is equal to 2 over 4 plus 1, that's 5 pi. When k is equal to 2, x is 2 over 9 pi. Let's do one more. When k is equal to 3, x is 2 over 13 pi. So hopefully you're seeing the pattern now, right? The key pattern here, these numbers keep getting smaller. The denominator keeps getting bigger, which means the number keeps getting smaller. It's creeping in closer and closer to 0. Now it's not gonna get there as long as we keep putting positive k values in, but it's gonna get really, really close. Right? So it's gonna look like this. Right? And just kind of work with me a little bit on the scale here. Right? If we put y equals 1 up here, it's gonna equal 1 here, and then here, and here, and here, and they're gonna get packed in tighter and tighter as we come in closer. So the curve is going to be doing this massively tight up and down oscillation. Okay, now here's the thing. If we were to repeat this exercise with -1, we would get the same thing, right? This would just be 3 pi over 2, right? And we would get this same behavior. So it's going to equal, it's going to equal -1 here, and here, and here, and here. And they're going to start to pack in densely here as well. And I'm going to try and do a quick sketch. You're going to have to just kind of bear with me. My artistic skills are seriously limited. It's going to be up and down, and it's going to spread out as it comes out here. Okay, now, and the behavior will repeat on the other side, right? If we put negative numbers in there for k, for example, you're going to get this same tight oscillation on the other side. And this is where we get into trouble, right? Pick a number over here to be the hypothetical limit, right? So we pick a number here. That'd be somewhere in the neighborhood of y equals 1/2. Well, pick any interval around here, and because this thing is oscillating up and down tighter and tighter, pick any interval around 0, and there's going to be a number in there. There's going to be an x value in there that makes the function equal to 1. In other words, it's going to be way up here outside of our interval. Right? So this limit doesn't exist either. Okay, so you can see, but one thing I want you to know is I had to make the function a little weird, right, to make that happen. And as we go along, we're going to talk about these things. Well-behaved function. It's kind of a vague math term, but we use it to refer to functions that don't have strange behaviors like this. Okay, so we have our kind of plain English definition. We've looked at a bunch of examples, and we've seen that it is kind of doing what we want it to do, right? It is giving us the values that we need. It's working when even at points where the function isn't defined, which was an important point for us to answer our instantaneous velocity question. So in the next lecture, what we're going to do, we're going to make this precise. We're going to come up with a formal mathematical definition. It's going to use those epsilons and deltas. And then we'll see how we can do some more formal proofs that kind of back up the results that we saw here.